learn calculus. Okay? So when reaction happens, most times you have two different kinds of reactants make a product. It would be okay for late law, for differential late law, that K, A, B, and N. That is differential late law. But when we do integration late law, it's more complicated because you have to do calculus to derive the equation. So for integral late law, we are limited only one reactant, not A, B, just only A. Okay. So that could be first zeroth order or first order, second order. Zeroth order means actually this is not affecting reaction rate, although it's there. First order means that is act as like a single molecule. If second order, A plus A. Okay, that's second order. If we involve 12 reactants, and if you want to use integral law, you may have to know calculus 4. Okay? If that's one single molecule, you just need calculus 1. Right? But here, you don't have to know. So this is late law when you have only single reactant, and if that's a first order, okay, you have first power, so it's first order. And the reaction rate is defined by change of concentration over time, because that is the reactant turn into something. We have a negative side. Okay. This is differential rate law. Now, integral rate law will be one of this. Okay. We can derive from here to there. Who want me to derive equation from here to there? You don't have to know, but I can explain if you want. Anyone in for that? No one? Okay, just only one person. We're gonna skip it.
Ben wanted to see it. I know you would have done it.
Okay, then what about this? Okay, so like when you see commercial, it's not like you buy everything, right? But you just still look at the commercial and then adjust the information, right?
Hmm?
I'm gonna go quickly derive it. You don't have to know, okay? So in calculus or differential equation, that delta is a time interval in the significant time interval. If you make a very small tiny interval, that will turn into D. A negative. You don't have to know, okay? Just you can say it. You rearrange as dA A, and I just move negative sign over here, K over here, dt over here. And then you do integration, okay? This is the integration sign. When you do integrate, there's a lower bound, upper bound. So we're gonna integrate from time 0 to certain time later, t, let's say t. Then constant here will be like we can do the same thing. T equals 0, t equals later. The integration of this guy will be k t over dt. This will be d variable over variable will be d ln a variable. So that will be logarithm a with 0t, and this side is still the same thing. And that will be ln and t ln 0. So that is integrated late law appeared right here. Okay? You don't have to derive it, but eventually you should remember this guy. So here for this course, you don't have to derive it, but you have to know this is integrated late law for first order reaction. Okay? although you don't have to know calculus, you still have to know algebra. So from this equation, you should be able to derive all over 3. Okay? Now, how that happened? Well, this guy, so this guy is the same thing as that guy, I just only just rearrange it. So from here you have to know, okay? You don't have to do all of this, but you have to know from here to, I can rearrange this as, when you have a logarithm property is, you can put this guy together. If it's subtraction, it becomes division, right? So that's one formula you have right here. And then when you have a logarithm, if you just change it, denominator or numerator, that is equal to negative sign. So if you cancel k from both sides, that's this equation. This is k. Another is if you inverse function of natural logarithm is exponential. So this is equal to at. Okay. I'm going to use this guy. At over a0 is exponential minus kt. If you multiply h on both sides, at is a0 e to the minus kt. So you need to know this guy. Let's go all 4. Okay. This is nothing to do with calculus. This is just algebra. So you have to know how to modify one from the other. Okay.
Can you clarify what your subscripts are over there?
This is time 0. This is later time. So this is 0.
0. Okay.
This is time t. Okay.
Thank you.
So let's look at this equation. So when reaction happen, so A turn into certain product, concentration A will change over time. How does it change? At t equals 0 initially if you put t equals 0 here, e to the minus 0, that will be e to the 0, which means 1. So at time equals 0, you have A t equals 0 is a0 e to the minus 0, e to the minus 0 is 1. So this is initial concentration, right? So if I draw a graph, at time equals, this is time axis. At 0 second, I have a0 concentration right here. As time goes, it decays exponentially. So that A concentration decay exponentially. Okay? So this will explain how concentration of reactant will change over time. It decay exponentially. You can pick any of this. Choose whatever you like. So choose each one to memorize. But once you memorize one of them, be able to derive the other thing. Okay? Because it will be difficult to memorize all 4 equations, right? It's not easy enough to memorize all 4, but memorize one and derive the other thing. So, let's say you memorize this equation and then you can move this one across or equal sign, then it will be this and minus k, right? So, from that equation, what you can do is call this guy as y, call your time as x. Then graph look like linear graph. So compared to this guy, here x-axis is time, y-axis is basically concentration of over time. Then you have exponential decay graph. But if I just change variable as y-axis is instead of constant itself, so this is like a AT, okay? Either AT or A, it's the same thing. This y value over x time is just linear. This is more convenient than that guy. Although that guy is more physical, makes sense, exponential decay, this is more convenient for problem solving. Okay? So so this is your y-intercept. It starts from ln h0, and then because this is a linear equation, negative k becomes your slope. That's why your slope is negative k. It's just linearly decay. Well, the original one is exponential decay, right? So that is true for first order reaction here. First order. If your reaction is second order, that means A with A become product. That's the second order. That's why you have in the late law, your A to the second power. That is equal to, this is definition of reaction rate. Then you can do similar calculus, integrate. Then in the end, you're gonna have integrate rate law like this. It's not difficult to drive if you know calculus, but I'm not gonna spend any more time to do that. This is actually easier than that guy. So what you need to do is memorize integrate rate law, okay? If you want, I can drive it. It's easy. So in this case, this is your y value. So 1 over concentration. This is your y value. This is y-intercept. So it starts from 1 over a0. And then still my x-axis is time. This time slope is positive k. Previously, first order was negative k slope. This is positive slope. So this line will just move up like that. Okay? It's easy to get confused between second order and first order. So you have to make sure remember correct formula. What about zeroth order? We have zero exponent over reactant, so actually it doesn't depend on the reactant concentration. Okay, that's what zeroth order is. So because Rayleigh law, if Rayleigh law is a to the 0, now this guy is simply 1. So practically Rayleigh law is just k only. This will be even easier integration process. Once you do it, this will be your integrated Rayleigh law. So your y-axis is just constant. This is your y, constant A. It change over time, and it has also negative slope. Okay. So memorize this. Memorize. So all together, if you compare those three. First order, zeroth order, second order here. So this is this disperion rate of reaction. So negative reactant over time. But second order has 2 here. First order, zeroth order has nothing there, right? So zeroth order, the concentration itself decay just linearly. First order, it decay exponentially. Third order, something looks like exponential. So if you see this decrease more rapidly, it makes sense because this one is proportional for just concentration. First order, this is second order, right? So if you square it, it'll reaction rate will be even faster. That's why it decays more fast and rapidly. Okay. First order, second order. Until Rayleigh, this is what you have to memorize it, all those formula. For zeroth order, it's concentration itself. We are using concentration itself. For first order, we are using logarithm concentration here. Second order is 1 over concentration. Okay? That's how y-axis has different variable. And then another difference is, well, once you memorize this guy is just initial concentration of same variable, initial concentration of same y variable, initial concentration of y variable, right? Only different thing is, for zeroth order and first order is a negative slope, so negative kt, negative kt. For second order it is positive kt. Okay? So if you see some pattern, it might be a little easier to memorize it. Whatever you do, as long as you memorize this formula, you'll be okay. And then from equation, you should be able to draw graph. They may not ask you draw graph, but they will ask you recognize. So they may show you one of this graph, and they may ask you either zeroth order, first order, second order. Right? So how do you know zeroth order, second order? Well, look at y-axis. If variable in the y-axis constant itself, and if it's linear, it's zeroth order. The variable is logarithm and also linear, that's first order. And the y value is 1 over a, and there is a line, then is second order. Okay? But what if you have a logarithm the y variable and the graph is not linear but like a curve? Then it's not first order. Okay? So determine first order, zeroth order, second order. Line itself, and the graph should be linear. Okay? And then once that's linear, look at the y variable. Okay? If logarithm first order, if constant itself, zeroth order, 1 over constant, that's second order. Okay? But you have to make sure graph is adjusted. So we have this reaction here, and then they have graph just like this, and it's a straight line. What's the reaction order then? Zeroth, first or second? Because this is straight line, okay? That's what you need to see. And then they said y-axis is a logarithm something. Logarithm constant. So that will be first order. Okay? You have to recognize that. And then they also said, so in the graph, y-axis is logarithm pH3, axis will be time. And those straight line with the slope negative value. So that is straight line and the slope is negative. So this slope is negative. So what is it? Length constant k? Well, this is length constant y, because you recognize first order. The moment you recognize the first order, you're gonna write rate, intermediate law as ln at is ln a0 minus kt. Why did you memorize it? Okay. This is y, this is x. This is y-intercept. Y-intercept. Then make this as slope. Okay. And then they say slope is this number. You have slope as negative k in your equation. So if you compare it, negative will cancel, k should be this number, right? That's why k will be this number. Unit. How do you decide the unit? Well, we can still use this formula. Anytime when you have a logarithm, the value have no unit. Okay? If anything has logarithm, it has no unit. So in your left side, your value have no unit, and this guy has no unit. To be equivalent, KT should have no unit. KT has no unit. But the thing is, you know time will have unit as second. Then make it K should have 1 over second unit, right? Why? Because KT should have no unit. So K will be 1 over second. So that constant has this unit. Now they are asking concentration of this pH3 reactant at later time, 70 seconds, and you are given an initial concentration like that. You just determine this will be your rate law, right? So what you know is ln pH3 equal ln pH3 at 0 second minus KT, and then K was already given over there, 0.0347, and time. But time is 70 seconds later, so this will be 70 seconds. This is 1 over second. And the initial concentration over here is given as 1 molarity. This is 1 molarity. So I know the 1 logarithm 1 will be 0. So I have negative 0.0347 times 70. That's my logarithm pH3. So my concentration later pH3 is exponential negative 0.0347 times 70. This will give you that number. Any question? So we are still doing first order reaction here, first order. When you have a graph for first order, if that y variable is just concentrate itself, then it will be exponential decay. Initial concentration decay like exponentially. Okay? You have to check what is the y variable. If that was like ln A, like the previous case, that will be linear decay, right? So using concentration as y variable, you have exponential decay. The unique feature of first order reaction is when it decay from original concentration half of that, it takes certain time, and then we call that time as half-life. And the variable of half-life is time that become half of molecule be gone or half of molecule remain. So this is a symbol for half-life, T and half. Okay. And let's say you have 150 more. What's your pressure? Okay. You have 150 torr gas. After half-life later, you're gonna have your pressure become half, 75. Again, if you wait another half-life, then that pressure become half again. Okay? It doesn't matter when you start, as long as you wait for half-life time, option become half. or concentration, pressure, whatever, that number we should have. Okay? This is only true for first order. If you have reaction in zero order or second order, half-life doesn't stay same. So for first order, half-life in the first interval, half-life in the second interval, the time will be same. But if there's a different reaction order, half-life in the first interval and half-life in the second interval will change. Okay? This is only true for first order. That is coming from calculus or some math stuff, but we are not going to cover that. So all you have to know is half-life of first order will be constant, doesn't change over time. Okay. So for first order, in your mind, you know the formula, okay? Integrate lay law is in your head. So you have to write what's the integrate lay law? Do you remember? Not yet, right? ln at equal to ln a0 minus kt, okay? You have to memorize right away, okay? So you're going to use this over and over. And if you just move this around, different form is a0, at, so you can drop t, but then you're going to assume that it will be at time t, okay? You can drop or not, it's the same thing. So if you wait time until half-life, then your concentration later will be become half of original concentration, right? That's the definition of half-life. If you wait for half-life, concentration will become half of original one. So if you put this guy on here, ln a0, this one is half of a0, and then you waited half-life. So you'll see this will cancel. You have ln 1/2 is equal to this. This is negative ln 2 negative k 1/2. So that will cancel negative sign. So you have half-life equal to ln 2 over k. This is algebra. This is not nothing. There's not calculus at all. So you have to be able to do it. And in the end, you could memorize it or you can drive it. Doesn't matter. In the end, you have to know this result. Okay. If you memorize it, it will be a quicker. Or you can still drive it. Either way, will be fine. This is just what I said previously. Half-life can be defined in a different reaction order, but just half-life of first order, that's important because that's a unique number that doesn't change. Okay? You don't have to know half-life of no. You should be able to know half-life of other things, but that's not important. Okay, so in this question, half-life is given as half-life is 20 seconds. I want to find out reaction constant K. Okay. How to do that? Well, K was ln2 over half-life, right? Actually, the equation we just derived was half-life was ln2K. If you have a fraction, you can switch those two variables. So you can just use this one as well. But they are asking K, use this formula. ln2 over half-life. Half-life is 20 seconds. So if you do math, you will get this value. Okay? This will give you 0.035 second. Why don't you try number 2? You may feel like all of a sudden challenging to do this, but why don't you try? Because they said the 75% disappear, that means 25 is still remaining, right? So, and then because first order we know that we can use this formula. If initially, so initially we have 100%. We don't know how many grams, how many molecules, but initially that was 100%, right? The later, only 25% remaining means later concentration or whatever amount will just 25%. So that will be lower than 0.25, equal to minus rate constant you got from the question 1. T is what they are asking. So if you solve for T, that will be 47. I want you to practice on this slide. So we did differential rate law is K times if we have two reactants react, and then whatever product we have. Rate law is something like this. So what if? So if A is like something like some molecule, let's say ammonia. Let's say this is chlorine. And then in other reaction, A is like alcohol. Let's say this is organic molecule, and this is some chloride. Let's say aldehyde. Because you have different reactant, reaction will be different, right? And the reaction rate will be also different. But what if I use some one molarity of this guy, one molarity of this guy, one molarity of this guy? Well, according to Rate law, if I put, even if you don't know the reaction order for each different reaction, if that's all one molarity, this will eventually become K, right? Even if I use all different compound, if everything is one molar concentration, then 1 over whatever order is just 1. It will equal K. So two different reactions have same K, just K only, but it should be different number, right? So in this case, K is something very unique number that describe different reaction. So although it's constant, we have to know a little more detail about K. Okay, because K is the indication of how different reactions happen. To explain K, someone suggested collision model. So K is a measure of how reaction go, how fast reaction go, depending on what you have. Let's say you try to find out some partner, okay, and then having girlfriend or boyfriend is like a reaction completion, okay. Now, to have your partner, you have to approach potential partner, right? And then have you have to initiate something, right? So if you approach into some wrong direction, reaction does not happen. So two reactions happen, like as a single two guy meet as a couple, you have to approach in the certain right direction. So that's what orientation is. When reaction happens, they should approach in certain right orientation. Otherwise, even if you meet somehow, reaction does not happen. Okay? Two reactions happen, you have to meet, but you have to meet in the right orientation. Okay? Also, another is you have to have enough energy. Even if I try with him, if my attempt is too weak, nothing happens. So my attempt should be effective, right? So you have to have any certain energy or above that energy. That is the activation energy. Okay? If you approach it a little less than activation energy, even if you have the chance, nothing happens. So you have to meet two conditions to make reaction happen. So this is the example. So chlorine meet NaCl, and they make a chlorine. This is product. So this is chlorine here. Now this guy has chlorine this side. It doesn't matter how hard you hit. You are not gonna get chlorine away, right? So you are not making any product. So this is wrong orientation. You have to approach in the right orientation. This is right orientation, and you have to be enough energy. Then you can take one of the chlorine out of this molecule. You make a product. But if this collision is weak, not strong enough, it will simply bounce off. Okay, it may chloride, but it will just bounce off just like that as single. Okay. This is another symbolic explanation of how reaction happen. Let's say this golf ball as a reactant. To reaction happen, let's say if this go over the here and then go the other side, we consider that become a product. To reaction happen, you have to go through a certain energy barrier. So you can consider this barrier as potential energy. Okay, potential energy. Now, when you hit the ball, you are imparting the kinetic energy. You don't have to know this formula, but if kinetic energy not enough, you may just go up a little bit here and just come down again, right? So you have to have your kinetic energy should be greater than this barrier to make a product. Now this is a more likely a feature of chemical reaction. Let's say I have reactants like this, and my product is switching nitrogen and carbon like this. That's my product. Okay. Then this guy belongs in the left side on the potential energy curve. This is my right side of the curve. When reaction happens, this guy should rotate. So when this guy rotate, this is a transition state, which means it's neither reactant nor product. It's kind of hybrid. So when you make so in the transformer, so you just change from one shape to the other shape, right? So this is the middle of shape. It doesn't belong neither of them. That's when you are on the top of energy barrier. Okay? We call that complex as activated complex. Activated complex is not neither reactant nor product. So when you are given multiple different energy diagram, this is where your reactant is, and the two reactions happen. You have to overcome the energy difference from reactant to product. This is what we call activation energy. We write as EA, activation energy. So you can decide which reaction will be fastest. That's determined by energy difference from reactant to top of the barrier. Okay? In this case, activation energy 15 kilojoule per mole. This will be 25. This is 20. So you can tell which reaction will go fastest. Obviously, smaller activation energy will go fastest. This is second fastest. This is the slowest. Okay.
Wait, can you explain one more time how you got the order? Are you subtracting?
We are
the
just,
one number from
we
the
are
other?
looking at the difference between a reactant
Uh-huh,
and transition state,
uh-huh.
because that's the height of barrier. So height of barrier is what determines the reaction rate, not reaction rate, they're constant. So this will be fastest. Okay, so largest K, next K, this is smallest K. Because this gap is from reactant to transition state. Okay?
Oh,
Although
okay.
it's on this side, still this is from the reactant to transition state.
I'm realizing that those aren't in order. The order is on the left side of the screen. That's why I was
Yeah, they're
confused.
slowest to fastest.
Thank you.
Yeah, slowest to fastest. So they may ask in the exam that draw all this energy diagram and indicate. So this will be your is it endothermic or exothermic? First of all, exothermic, because your product is lower energy than reactant, so that difference of energy will be released. So it's exothermic. So they will ask you draw reaction profile for exothermic or endothermic. So this is case. If they ask exothermic, you draw this, and also you're gonna write as this difference. So you indicate with arrow. So you can use just a dotted line between those two states, and then use arrow, and that Next arrow, this is the activation energy. You have to indicate activation energy. Okay? Especially activation energy for forward reaction. Right? When reaction proceeds from reactant to product, this is activation energy. But if your reaction happen through opposite, then your activation value is from here to all the way top. So you can write activation energy for reverse reaction using this arrow. Okay? And the energy difference between reactant and product is heat of reaction, delta H, heat of reaction, or reaction energy. And although it's not here, you're gonna have to indicate energy level. I want you to write down this on your slide. Energy level from right bottom to all the way top, and now all the way to reactant. This is energy for reactant. Okay, this is energy for reactant. Now from the bottom of here to product, that's energy of product. From bottom of here to all the way to top here, this is energy for activated complex. And also indicate this top here as transition state or activated complex. Okay? So you should be able to draw this whole graph, whole diagram with indication of arrow and value. Okay? For this is exothermic. For endothermic reaction, you have to draw the reactant side is lower than product side, and then write down all over that over here. Okay. They use this question in the exam, so they may go again. Not every time, but they often ask. So we just said the Lake constant the characteristic of certain reaction, whether reaction between this guy, reaction between alcohol and aldehyde. This will describe how reaction could go, how fast. And then we said if they all put in the right orientation, that will make reaction faster. And then if they had approach with higher energy than activation energy, it will be fast, right? So taking all those factors into account, RNUs come with ideal equation just like this. Okay? This is what we call RNUs equation here. So if activation energy is higher, reaction should go slower, right? From this equation, if this is higher number, then this will be more negative. If this is more negative, exponential function will be smaller number, then make it Lake constant smaller. Okay? And also if temperature goes higher, then this number will be smaller. Negative small number means on exponent is a bigger number. Then make K as a bigger number, right? So at higher temperature, reaction goes faster. That's why we have to put our food in the refrigerator to keep temperature low. Okay? So reaction goes slow. Now we said the reaction can go faster if we approach the right orientation. So A, this factor is what is connected to the orientation. So A is called RNA constant or frequency factor. That is indication of proper orientation. Okay? So we derive how A will be given, how we got this equation from the higher level chemistry. In Chem 2, we don't derive this equation. Okay? As long as you understand and if the equation makes sense, when the vector is higher, if slow, that's just algebra, right? So if you understand that, that's enough. Okay? Now I'm going to explain this graph a little bit. For given temperature, like room temperature, you have lots of molecules here in the air. They move all different speed. Okay, some molecules move a little faster, other molecules move slower. So if I just draw this distribution at certain temperature, some molecule, so this is kinetic energy. Kinetic energy is related to velocity, okay? Because formula for kinetic energy, 1/2 mass velocity scale. So some guy will move slower here, so lower energy. Some guy will move faster. They move at all different speed. So if I draw this population, it will be like this. This is distribution. Most of them will move at this speed. So it's like if you go to when you drive, if there's a speed limit at 70 mph, most car go at that speed, right? But there's a certain car always go faster than speed limit. There's other cars slower than speed limit because they have some reason to go slower. But most cars will go at that speed. So temperature is like a speed limit, kind of speed limit for molecules. So you increase temperature a little higher, then everybody move faster. It's like a speed limit from 70 mph all of a sudden 80 mph. Then most of the car will go faster, right? So fast, some cars are going at 100 mph, something like that. So overall, that distribution will move just like this, red line. So most molecule move from here to a little faster, then make it. This is the activation energy right here. At low temperature, only this portion of a molecule will be having a higher energy than activation energy. When temperature higher, you see more population. You look at the red line. You have more molecule have that higher energy. This is why changing temperature will increase population. That is reflected on this equation. So this is what they decide experimentally, theoretically, and this is how they derive these equations. Okay? We are not going to do derivation, but as long as you understand this concept over there, that will be good enough. Now this is more relevant to you in this course. So this is RNP is what you have to memorize, and then we can do algebraic manipulation. Let's take logarithm both sides. Then log k equal to log a e to b over rt. Property logarithm is if you have something multiplied, you turn it to addition. And also, if you have something as exponent, you can come in front of logarithm. And also, natural logarithm of e is equal to 1. So you end up having ln a minus ea rt ln k. Therefore, RNS equation can be modified into this form. Right? So you need to know both. And the reason this is useful is, again, you can do similar or linear plot. Consider ln k as y value, 1 over temperature as x value. Then you have y value as ln k, and the ln a is your y-intercept right here. And then your x value is 1 over t, and then your slope is negative activation energy over r. Okay? So I want you to recognize graph. This is also another convenient formula that you may have to use for some question, some problem. From Arrhenius equation, you just derive this equation, right? So you can say ln K will depending on temperature. So sometimes they will give you different rate constant at different temperature. Then what you could do is, my rate, this is rate constant, not uppercase K, not equal constant. This is a rate constant. So at different temperature, you may have this. In other temperature, you would have same formula with just different temperature. Then you just subtract it. Okay, one from the other. So ln K2 minus ln K1. If you subtract it, ln A go away. EA RT2 because you subtract RT1. Then this will turn into ln K2 over K1 because that's a property of logarithm. Here, if I just take, why don't I write one more time? EA R negative 1 over T2 plus 1 over T1. Okay. So then you end up having this final formula. Okay. You can derive this final result from Arrhenius equation through logarithm expression to here, or you memorize it. But I encourage you can derive it. Okay? Because if you memorize too many formula, your brain not. Okay, last slide. So they are asking calculate activation energy. And we are given temperature and rate constant. No, what is that? Rate constant is okay, and okay, this is frequency factor. Okay, yeah, we are given frequency factor A is this number, P is that. Okay, then you can use Arrhenius equation. Arrhenius equation is K is A e to the negative activation energy over RT. So you can plug in all those numbers. A is given, and the exponential activation energy we don't know. That's what they are asking. R value is what? R value is you have to memorize gas constant. What's gas constant? This number. R is 0.082. What's the unit?
8.34.
No, this is right. This is right. Gas constant. That is the gas constant you use for ideal gas from here, right? So this unit is pressure, which means atom times liter divided by mole divided by K. This is the right gas constant. We don't use this one in Chem 2. This is for Chem 1. In Chem 2, let's look at this. When something in the behind the logarithm or behind the exponential, they do not have a unit. Okay? Remember this. If something is behind the logarithm or behind the exponential, they shouldn't have any unit. Then make it, this guy should not have any unit. No unit for this guy. Okay? No unit for this guy. But I know actual energy has unit. So that will be kilojoule. I know that R has a unit. That will be K. So I should have a unit as kilojoule over Kelvin. Right? And then there should be more somewhere. A kilojoule. Let me see. Oh, yeah, right there. So gas constant is 8.314. This is actually you have to memorize it for Chem 2. And the unit for that is let me see. Yeah. I'm gonna change this guy's joule. And mole is although it's not clear from here. Because activation energy can be given as joule per mole, and temperature will be K. Then R unit with this. So actually activation energy is given as joule per mole. Okay. All right. Go back to. If I write again, K is A, E, E, A, R, T. So K was 17 second per second. A is 1.5 and 11 per second. E, activation energy. R is 8.314 joule per mole. Okay. Temperature is 25 Celsius, which means if you add 273 to 98 Kelvin. Okay. So from here you could use 17. So this unit will cancel. Divided by 1.5 10 to the 11 equal to e to the EA over 8.314 times 298. If you take logarithm both sides, natural logarithm, equal to logarithm E minus EA of these two numbers, that anything in the exponent can come in front of logarithm, and the ln E is equal to 1, so you have negative EA 8.314 times 298. So comparing this and that, my activation energy will be negative 8.314 times 298 times ln 17 over 1.5 10 to the 11. Okay. And the unit should be joule over mole. Okay. And then if the number is great, very big, you want to convert that to kilojoule. Right? Either joule per mole, joule per mole will be okay, but in this case, number is big. Convert to kilojoule. For second problem, if you look at here, there's a rate constant here. Rate constant. There's temperature. For this reaction, there's another rate constant. So I'm going to have to call first one is K1, second is K2. And then there's another temperature here. Can I erase this? So in this case, when you have a reaction, there's one temperature, so I'm going to call T1. There's another temperature, I'm going to call T2. So that's K1, that's K2. And they're asking activation energy. So any temperature rate constant should remind you RNU's equation. But when you have two of them, you are using this guy, ln K2 over K1 equal, what's the formula? 1 over T, K2, 1 T1 minus 1 over T2. I think it is 1 over R. Is that right? I also something else. Yeah, I missed EA. EA. So ln K2 is what? 4.9. 4.9 10 to the minus 4 over K1 is this number, 2.6 10 to the minus 8. Activation energy, gas constant is 8.314 joule per mole per K. And I have 1 over first temperature is 300 Kelvin. And second temperature is 400 Kelvin. So to find out activation energy, because that's what they are asking. Activation energy is ln 4.9 10 to the minus 4 divided by 2.6 10 to the minus 8 multiply 8.314 divided by 1 over 300 minus 400. That's our active energy. That was last slide.